All right. Well, thanks very much for hosting us. I'm going to jump into commercial HVAC systems, and then I'm going to feed into, pardon me, we're going to feed into the lessons on central heat pump water heaters. So first, I'm going to go quickly. And so a lot of the lessons that are in these slides are from these booklets that are free downloads, just so you know, over at Redwood Energy's website. Now, jumping into it, commercial buildings. This is a big load. 16% of carbon dioxide emissions in the United States, 10% of natural gas use, big one. So here's some prominent engineers. They just got to share the details. Almost all of our gut retrofits are able to go all electric. For major renovations, we're able to guide the client to go all electric by providing technical solutions that are cost comparable and have a similar life cycle savings potential that are of equivalent gas systems. And we can make these arguments pretty well. So Ted Tiffany, Gutman Blovet, John Gautry over at Integral. Higher end developers and universities are absolutely 100% on board with electrification, no question about it at all. Taylor Engineering, prominent folks. 3 to 4 years ago, only 10% of our projects were all electric. Now about 90% of them are. Now in California, the existing, and I recognize every state's different. California has like 12% of Americans in it, and I have good stats on California. So the lesson I want you to learn from here is the green is heat pumps, orange is gas furnaces, and it's different by climate. So PG&E is Northern California, SoCal Edison is Southern California, San Diego Gas and Electric, the furthest south. You can see how as the climate gets warmer, heat pumps jump up to 52% once they work out climate-wise. And that used to be the case that there's only single speed heat pumps. Now there's inverter controlled heat pumps that I'll share with you as we go. And they can do in any climate. So roughly what we're looking at in single zone products, 59% package, 13% split system, 8% just little wall units, and 7% packaged units. And then only 6% are the big building multi-zone. But big buildings have a disproportionate number of things in them. So it can be a very similar amount in square footage, big buildings versus all the small buildings added up. So talking about these ones, Stat Sanborn over at the Smith Group says, the biggest market, if you want to make a move on actually getting gas out of commercial buildings, is to target the rooftop package units with easy retrofits. And it is easy. There's tons of these products that are made that are cold climate now. So nice little case study here. This building and the Berkeley Mental Health Services, sorry, I think Berkeley might be misspelled without an E in there. Apologies. So it's a zero energy retrofit of 1925 building. Very little is done to the exterior because that's generally not easy to do with historically protected buildings. So instead they went for efficiency with the heat pumps, 2 Daikin Rebel heat pump units that were packaged up on the roof with heat recovery and electric resistance backup and some fancy thermofusers for diffusing out the air. Okay, so this is a retrofit that was done with the packaged ones. Now I'm going to go into variable air volume. So these are VAV boxes. Air is moving through them. They've got dampers to make it variable. And you can heat these with water coils or electric resistance coils. It's not very efficient to circulate hot water, particularly if you're doing it with electricity, heating it with resistance. So resistance coils were an efficiency move, but because it still causes, essentially it's an electric resistance space heating system for a whole building, it has big grid spikes, not a great fit. So instead, going with a heat pump that feeds into that hot water loop, not an electric resistance boiler. So Reinhard Seil there says, hey, in most cases, typical heat pumps that can produce 120 degree water will actually work just fine in buildings with an existing boiler reheat system like that VAV box, as long as they have 2 row coils, which means enough surface area to distribute the heat, which most buildings do. So it's just, there's a couple buildings in this picture here that they did. If you had to get to 180 Fahrenheit, this is an example. This is a 2-stage process where you go from -30, say up to 70, 80 degrees Fahrenheit, and then take a water loop heat pump, water source heat pump, pull the heat out of that and take it up to 180 Fahrenheit. Franson did a nice slide show for me once, and so I use this as their image, but basically air source heat pump, that's for cold climates, and then a water loop. Different example of HVAC here. So they took out like 35 tons of air conditioning, and they put in, I think it was 18 tons or so of VRF, variable refrigerant flow. And then they also put in the Ventacity HRV. And the heat recovery ventilator meant they were able to cut both the space cooling and space heating loads in roughly half. This heat was coming back in. Fantastic. So this meant that they could put in a space heating system with no increase in service because they had a whole lot of capacity. They reduced all the air conditioning on top of it. Now, lessons learned from a project that we led. We're going to transition out of commercial buildings for a second and start going into the boiler talk. So these are individual tanks that are up on the roof, kind of far away from the apartments underneath them. There's a whole like heat pump garden up there, you might call it. Now we modeled this at being negative 9%, like 9% above zero net energy. Instead, we got 17% below. And we're like, what happened here? Lessons learned. So here are the three major loads are hot water in orange in the bottom, heating and cooling in blue, and then plug loads and miscellaneous electric loads, right, in yellow, and then the other stuff like the cooking and then refrigerator and then all this rest of it's all added together. So the basic problem is that domestic hot water we were seeing is about 1/3 electric resistance water heater. And we were seeing that in the space heating, that's way above what we expected because there was an electric resistance crankcase heater as a wire metal, like just metal wire, pardon me, wrapped around the compressor that was supposed to keep it warm enough to keep refrigerant and lubricating fluid from mixing. Okay, now these tanks up on the roof, I'm going to go into the water heaters. Tanks up on the roof, they had a recirculating system similar to boilers. And we got to see that when you bring warm water back to these individual tanks, just like all these tanks with this kind of refrigerant, but just generally, anytime you're recirculating hot water into a heat pump, you have really low efficiency. And so we're seeing the energy use here drop from recirculation when we put in occupancy sensors, replaced occupancy sensors, which are going on all the time, and put in demand push button. So now it wasn't a constantly recirculating system that was using tons of heat pump energy, because on the left-hand side, you see that's heat pump energy being used, watt hours, and see how the energy drops when we put in the push button sensors. That's because there's radically greater efficiency if you don't recirculate the hot water straight into the heat pump. Now, winter to summer, you can see in orange, that's the electric resistance, quote unquote, backup. So on the left-hand side, that's winter. On the right-hand side, that's summer. In blue, that's the heat pump operating. And we found that the heat pump operating was only a little bit more in the wintertime. And we were able to figure out like, oh, if we stored enough hot water at 140 degrees Fahrenheit instead of 120 or 125, we don't have to have electric resistance at all, which is the basis of the new 120 volt heat pump water heaters, the 500 watt ones that go in, that you can plug in into any outlet. So we did a whole bunch of research, turned it over to all the different heat pump water heater manufacturers and said, this really would work if we just stored the water hotter and then had integrated thermal mixing valves, which is that little black doohickey on the side of it, mixing valves there. Okay, I want to show you, we learned this lesson. These big heat pumps, which had all this recirculation water coming through, barely any difference between the outgoing water temperature and the incoming water temperature, like a degree or two. And we got very low coefficients of performance. It was designed to be 2.4. Lower than that is bad, and better than that is good. So we found that if we were doing both air conditioning and domestic hot water at the same time, we could get a coincident coefficient of performance of about 3, better than what we expected. But for the most part, look over on the right-hand side. You're not going to find too many numbers that are above 2.4, and lots of them at 0.4 and 1.85 and 1.26. Occasionally, oopsie, you can see under simultaneous, that's where we get some of our better numbers, but it was rare. And so it was just something to say is that if a product truly had balanced simultaneous heating and cooling, this would be a good product. And there's lots of those applications, but an apartment complex doesn't have that balance just inherently. So then here we can see over at our project in Gilroy, this is a central heat pump water heater made by Colmac. So it's using R134A refrigerant. You can see electric resistance in gray, and you can see the heat pump usage in orange. And you can see some problems we had with electricity, but basically the COP 1.67, that's bad. We remodeled it at like 2.4 or better. So, and the whole system is at 1.48 because there's recirculation and electric resistance thrown into there. So not very good. This is supposed to be like a high performance efficiency, oriented heat pump system, and the design's not so great, but that's always an issue. Fundamentally, getting low efficiency, but not out of the sand and heat pumps. So this is a different field study, and you're seeing COPs on the left there. Note that these numbers, the worst is at orange at 2, which is the recirculation hot water. Okay, but all these other numbers are at 3 and 4 and 5. This is at different systems because there's like 3 different systems in the building, and it's during different seasons from left to right: winter, spring, summer, and fall. And we're seeing not very different efficiencies in the seasons. We're seeing differently efficient systems, but not, when the system is well designed, that's where we're seeing COPs of 4 and 5 year round. So that's one of the reasons why Albert Rooks' system here can make sense, because it comes pre-engineered, so it's a good design. Everything's balanced and plumbed right, not wrong, because there's infinite ways of doing things wrong. Less ways to do things right. So here we have Sandin's, the same heat pump that I like. And this is a tiny house development that we supported. So I'm going to show you these are 7 tiny houses. They're on one Sandin and with 1 tank of hot water, and it's on a manifold, not recirculating. So the water goes out at the efficiency that it was created, and there's nothing that ever degrades it. And all the tenants are happy. We just got that reconfirmed with them. Happy tenants, all 7 of them on a manifold. And you can see that the efficiencies, the COPs down on the bottom, COPs of 6.86, 3.18, 5.09, 4.77, 5.24. So our weekly average there was a 4.2. They're not all using the same amount of hot water in the same ways. Oh, sorry, this is different days. Pardon me. Every day is different, is what I mean to say. The system is not always, if you use less of the energy, anyway, I don't want to go into COP explanation. It's just that it's different each day, and that's normal. Okay, oopsie. That's 4.2, right? And we have daily COP not accurate due to incomplete heating cycles. So we're still getting data on this and try to refine it. So this is the other set of units. We have essentially the exact same average, COP of 4.2 over a week as we have on the previous set of 7, but it's not the same data. That's fun. And it's also almost twice as much hot water use. The previous one was 13. This is 28. So with that sort of setup to say, like, design matters, but so does usage behavior. So you're not going to see any one system looking identical to any other system. You always need to have a fair amount of data. You need to be able to average systems and compare them. Albert, unless people have questions, of
Yes,
course,
sir.
This is your chance now to start digging deeper into well-designed central heat pump boilers.
Well, after pausing for questions, I'm going to do that. And Sean, a lot of this information I actually hadn't seen before. It's really super interesting. I think you've got field data that we need to see more of.
We have more of it too. I realized that we could do a better job of sharing it, but some of this is not published because it's fresh out of like our field research now. But this stuff is published. Some of the other ones are not.
So we struggle even on the Sandin, single family application. We continue to struggle with recirculation loops, right? Because it has the same effect in a single family, 1 heat pump, 1 tank. And I've just not seen those numbers presented that way. That's a big deal right there. That is really, really helpful. I'm going to steal a screenshot. Boom.
And I sent you the slides also earlier today.
Thanks.
But I think this is one of the most powerful before and afters, because we can turn off this recirculation. This was an optional recirculation system that was going off because the sunlight outside changed and a bird flew by and a dog ran by and there was a mirror in the bathroom and who knows what. But we had like 60 tanks that we're looking at that all had destroyed COPs, and we had to go through, and every single one of them got the turned into a push button. And we learned the people only use the push button about half the time when they're in a bathroom.
Oh, well, yeah, that makes sense. So, okay, so Jay, let's keep an eye out for questions coming up, and questions on this as we go are just going to be great. Sorry, I'll do a quick screen share there. Okay, are you ready for me to grab the screen?
I am. I'll stop share and take it away, my friend.
All right. Okay, great. So just backing up a little bit of introduction, who just presented, great visionary. We're really lucky to have him in our industry. That was Sean Armstrong with Redwood Energy. Always a pleasure. Thanks, Jay. No one needs to know where the restrooms are, because we all know where we are. My name is Albert Rooks. I'm founder of Small Planet Supply and Water Drop Systems. And Water Drop Systems is a branch of our business. We developed it within Small Planet Supply, and we did it because just the simple lifting of cold water to hot water and domestic hot water applications became more and more interesting, and more development became possible. And we found some really good solutions, been working really closely with folks from the Advanced Water Heating Initiative, which is a group of publicly funded utilities and power providers, including Bonneville Power Administration, SMUD in Sacramento, Southern California Edison, Seattle City Light, BC Hydro in BC, Canada, a lot of utility partners doing a lot of years of studies trying to figure out how to do this transition from fossil fuel to heat pumps and get really, really good results. And part of the results, if the results are verifiable and continuous, they can create budgets to incentivize them. And they want to incentivize something that really works, not something that looks good in a plan, but the actual site performance degrades, kind of like what Sean's showing. So it becomes a real process and a real question about how do we achieve that. And part of the answer, there's a number of answers with this, but one part of the answer that really got us excited was pre-packaging and building things out so that they can arrive to site completely ready to go. Great. I jumped a slide there. Sorry. Okay. So there's the slide that I want to be on. And so part of the solution was an adventure in pre-design and pre-packaging to cover two different things. One is that in working with Sean, we and others in the industry, someone will bring us a building to develop one of these domestic hot water systems using the Sanco 2 heat pump. And we would typically, in a commercial application, use many heat pumps and a few tanks and develop a design and a sizing to suit the building, and then recommend it for a site installation. At that point, we're offering some consultation and a design potential to an installer. And there's multiple people on the team, right? There's people in the design and the energy modeling, and then people in the mechanical design, getting everything to line up correctly, making sure there's power to the building. And then there's an installer, and then there's someone starting it up, and then hopefully everything is kind of arranged right. Over the years, what we found is these Sanco 2 designs work really, really well, and we're able to get a really good level of efficiency out of them as long as they're installed right. Installing right is a big capture because there's a lot of things going on. And when you step back and you look at this at scale, what we're doing is we've learned how to craft a solution for each building rather than apply a programmatic solution across a wide range of buildings. Two different things. Craft solution means everybody on the team has to know their craft. They apply their craft on that particular project. Whereas a programmatic solution means that we have a catalog of solutions. We look at the building, select the right the right intersection between catalog and application, and then apply that. And so that's really what came out of a lot of the early research. And so our company just became really excited and curious about this. So the solution that we developed was to develop an entire company that would take a building from anyone that would bring us a building and help the building get sized, help the building become turn into a plant size, pre-engineer a number of plants in single delivery or semi-assembled solutions, which we'll see here in a moment, and then offer that up to as a completed product to drop into the site. And then that would make the installer and the site assembly a really limited activity, which therefore limits risk and confirms performance, and then just kind of carry that through to a company and a service. So that's what we've done. Picture on the right is a big skid project going in California. That's one of the two skids that create a pair of skids that operate as one water heater, just landing on a roof in California. We developed two systems. We'll look at this system first, which is the package skid. So there are about 7 sizes, and these 7 sizes can serve a range of buildings from very small to very large. And it is a possibility where we just look at the building load and say, well, that's this water heater right here. And this is literally a water heater, or it's a boiler. It's the new boiler that's able to just set on the side of the building. Cold water comes in, hot water comes out. After it goes through a mixing valve, out to the building, the recirculation loop will bring it back into the system, and the system will receive the recirculation and isolate it away from that primary storage to avoid kind of that degradation of COP that we saw in Sean. This is probably a great example to look at this simple cycle of how these systems are designed around this little SANCO2 CO2 refrigerant. And the SANCO2 CO2 refrigerant has a lot more potential than the tall unitaries that we used in the project that we're going to look at earlier, and the project that Sean was talking about where we had that garden of heat pump, hopefully with decals of green ferns and forestry things up in the garden area on the heat pumps. But essentially the design is the heat pumps are there on the left-hand side of your screen on the back. And then those heat pumps will take cold water and lift them 100 degrees, always roughly 100 degrees, from 50-degree incoming water temperature to 150-degree leaving water temperature. And that water will go into that big white storage tank in the back. That's the primary storage. So all we're doing is taking cold water in from the front of that building connection in the lower forefront of the picture, running it into the white tank in the lower level to create a stratification layer. So we've always had a source of cold water for the heat pump. And this is important to kind of keep the efficiency running. Send it out through the heat pumps, lift it 100 degrees, and then bring it back and drop it right into the top of that tank. So what happens with heat pumps and domestic hot water boilers that Sean was talking about was when we take that water that's a full temperature, we mix it down across a mixing valve, and then we send it out to the building through a recirculation loop. We're sending out roughly 120-degree water. We're sending it around the building, and then we're bringing it back to the system. When we bring it back, there's always a loss, so we can expect the return temperature might be around 110 degrees. So think about it. If we brought that 110-degree water back and put it in that primary tank, and we did that over and over and over, especially when everyone's asleep and there's no domestic hot water use, then essentially all we're doing is lowering that tank temperature from 150 down to 110. And because we're looking at the actual energy consumption, we're just losing energy without actually getting the benefit of domestic hot water. And that's where you take a hit on your COP as you're looking at the system. So there's a way around that. And the way around that is to actually move that recirculation return to a separate tank and isolate it and treat it as its own little function. So that gray tank in the middle, which in this skid is a Bach 119 gallon tank with a little electric water heater element in it, is called a swing tank. And it's called a swing tank because the temperature in the tank will swing high and then it'll swing low. And then it'll swing high again and then low again. And so what we do,
Albert, may I interject?
Yeah, please.
I just want to note that you did put a heat pump in that function, the recirc system.
Yeah, so when we look at
Delano?
the project, you'll see that it's actually a heat pump in the Parkside project. Right. So we'll walk through this last little section about kind of how a swing tank works. So in a swing tank application, the swing tank application is to prevent those losses when you have a recirculation system. If you don't have a recirculation system, you don't need a swing tank. So what it does is, instead of pulling water out of the top of that big white primary storage tank at 150 degrees and sending it out to the building, we'll send that water out to that swing tank. It'll go into the swing tank and we'll heat the whole swing tank to a full 150 degrees. And we'll keep it at 150 degrees as long as water is being pulled through that swing tank and people are using water in the building. As soon as they stop using water in the building, then we've got a fixed temperature. Okay, so now let's look at the other side of that transaction. We send water out across the building, it doesn't get used, and it comes back. When it comes back into the swing tank, it always comes at a little bit lower temperature. During the day, when people are using hot water, there's enough of the high temperature fresh water coming in from primary storage to keep that tank, that swing tank, at full temperature. But at night, when people are not using domestic hot water, the system is stopped. So we're giving water out of that swing tank, losing 10 degrees and bringing it back. And we do that for 5 or 6 hours, and we'll actually lower the temperature of that swing tank from 150 well below the mixing temperature of 120. So now we've isolated that loss away from the primary storage. So the heat pumps and the COP are going to be very happy. We're not damaging the system. And all we got to do now is that when there's a call for water, we got to make sure that we lift that swing tank temperature back up above 120. And we do that by just using an electric water heater, or in the Parkside apartments, a unitary heat pump water heater. So in this case, we'll have a heat pump heating another tank of water that's being reheated again by a heat pump. So it's a heat pump on a heat pump. And I guess we throw enough mirrors in there, it can be infinity. So in any case, that's how we isolate the swing tank losses away. In the Parkside apartments, we wound up developing a system where we could build the heat pump array in a prefabricated shop and then take it to site to get it installed. And so that's exactly what we did. We find that we're coming into this building after construction has already started, and we've got some limitations. We designed a system around these droplets where we can cover a lot of building sizes, but we don't necessarily need to look at that right now. We'll take a look more at the actual project and come back and look at the sizes. But be it to say, we can cover very, very small buildings like this building, or very, very large buildings. So now let's look at the building. Here we come. We're looking at this new project, and we're actually capturing this project midway in construction. Here's this collection of 5 buildings, which are small buildings, and each building has got 4 apartments and 8 apartments in it, 4 low and 4 high, or a mixture close to that. And it's already designed, and it was designed for a gas boiler. And so now we got to apply a heat pump into it. So on the left-hand side of the screen, in kind of that center section by that number 5 in a circle, you can see that these were the closets that were set up for a boiler. And that's really the space we have to work with. And the interesting thing is, with a central heat pump plant that is going to serve a building like this or bigger, you generally need more space, because with a boiler, a gas-fired boiler, right, it's not much of a thing, really. You've got a tank of water and you got a burner below it, and you got a pipe of gas, you bring in the gas, you light it on fire, and you got energy to lift the water. And so it doesn't really take that much space. If you need to lift more water or push more water through, you just add more gas. With a heat pump, we have to step back and think about it, because heat pumps have a much slower recovery. And so it's really all about building storage ahead of the use. So when we build storage ahead of the use and we need the heat pumps to serve that kind of a load, we need a little bit more space. So we were really struggling on how we're going to fit these heat pumps into these small closets that are also going to handle service panels and fire alarms and just, you know, all the other things that these mechanical closets would be working with. So that's where we kind of crafted a solution based on understanding what the load is. So in understanding the load, the typical tools that we would use would be the EcoSizer, which is a relatively new tool. It's about 2 to 3 years old at this point, and it allows us to enter a lot of data and come back with a system sizing. And the system sizing in this particular building was rather small, and it's on the small side of the EcoSizer. And the EcoSizer is a new tool, so we need to do some separate checks. So we run some sizings in the EcoSizer. We start understanding really maybe what the building needs. And then we run another separate set of calculations to make sure we're really within the range of where the building is going to be operating for its domestic hot water plant. But we come up with a sizing. The sizing tells us kind of what kind of plant we need. It tells us how much heat capacity that we need, or heat pump capacity, and then how much storage we'll need in the additional swing tank. And then we average that storage across the building types, so we can make one plant and prefabricate it and deliver it down into the building. This is the project in mid-construction. So these are the spaces that we're working with. And so on the picture on the left, that's the actual closet where this equipment was going to go. And picture on the right is the space inside of the closet. And in that closet, we've got to fit about 31,000 BTU an hour of heat pump capacity. We've got to fit a swing tank. And then we've also got to fit a primary storage tank. And to make it even more interesting, we are helping to develop a full M&V package to confirm how this building performs and how the plant performs, and whether it delivers the planned COP of something above 3, and whether our design and our sizing has enough domestic hot water capacity to serve the building without running out of hot water. And so we started that work, and these are the tools we're given. So this is where we create this new system of an adaptable pre-manufactured solution for existing buildings and buildings that just need something that's a little more friendly and easier to adapt to. So we take our 2 Sanco 2s there on the left, and we create a racking system. And because in these systems, in site-built systems, part of the learning from the Advanced Water Heating Initiative is that pre-manufacturing is key. Because as we pipe these together, the choice of the check valve and how the check valve is placed, how the strainer is oriented, all of these things are really important to get right to have the system operate. Each heat pump is using CO2 as a refrigerant, so it's super efficient. It's got its own internal water pump. It's a variable speed water pump. The compressor is a variable speed because it's an inverter driven system. So we can do a lot, but we've got to make sure that it's piped and operating in the optimum performance in order to get that high COP, because each one of those heat pumps is only going to use about 1,000 watts when it's in operating condition on a day like that in Central California. And so it becomes really important, all those components and how it's piped, and have that deliver on site and go into the building and get started up without any mishaps and any questions. So even
I want to interject, Albert.
Yeah, please.
Because I didn't mention the field data, but you brought up how important it is to have a variable speed pump. So you have variable speed compressor, awesome. The pump, which allows us to meet more water demand or less water demand, as opposed to just always being on or off. It's a big part of the efficiency of this system that you've put together that we keep on seeing. If we have non-variable speed, single speed pumps, it wrecks the efficiency of the system, because people don't have single speed demand, like they're all sorts of different demands over the course of a day. So anyway, I just wanted to re-emphasize that point. That's all.
Yeah, exactly. And so really it's the heat pump itself. And then we've got a system between the heat pumps, the primary storage, and the swing tank that allow the morning peaks and maybe no activity or during the midday, and then the afternoon peaks. And everything is really set up in a way that operates at the most efficient that we know how to make these things right now. So we created this system, and we created a design, communicate the design out, and then built it all in the shop and sent it down and placed it on the outside in these pads. And you can see in the left-hand picture, we've got a single power landing for both heat pumps. There's a control on the inside of the building. I think we'll see that here in a little bit. And in this picture, we've got a swing tank on the left, and that's an actual unitary heat pump. And it took a little bit of work to make that work. These unitary heat pumps handling a larger building have smaller ports, 3/4 inch ports. So we had to do a lot of calculation to make sure that we could support the water flow in the, I believe, type M copper, to make sure that the copper wouldn't be deteriorated by the high flow and the reduced diameter, because you can see it's kind of a mixture of like 1.5 inch piping and 3/4 inch and 1 inch piping. And so the larger diameter of the piping, we get a little less resistance and a little longer wear and tear. And in this system, you can see that we've placed the recirculation pump, and we've got a lot of room around that piping, because what's going to happen next is that a whole lot of metering is going to come back on site and get cut into this piping arrangement. And the reason it's so kind of spread out and placed against the wall is to be able to have enough pipe length to smooth out the flow and get this kind of nice lamellar flow, so that the flow meters are reading an accurate flow. Normally, it doesn't look as large as this. We can usually fit it into a tighter space, but we're going to gather a lot of data with this system.
This would be a chance to thank our financial sponsors, the CalNext program and SoCal Edison, who have funded this as both an installation and a research site. Yeah, and also the tech program, which really underwrote the entire cost of the system to go into this project also. So picture on the left, you got a 120 gallon or 119 gallon tank on the right-hand side. That's the primary storage. And on the left-hand side is that unitary water heater. So that's acting as the swing tank. So recirculation, so water comes in from the heat pumps into that primary storage tank on the right. And then as there's a call from the building, it'll come out of that primary storage tank through the piping into that recirculation tank or the swing tank. And it'll hold in the swing tank. And as there's a call for water in the building, it'll come out of the swing tank and go out to the building. The recirculation loop will return back to that swing tank. And then as the internal temperature of the swing tank cools, then the heat pump function of that unitary heat pump will turn on and lift that temperature back up. So we've got a really nifty little system that's really pretty simple to put together, and we can just receive this racked heat pump configuration, set it on a pad, connect 2 water pipes, and bring out a power landing. And it's pretty simple to operate. Once we get it all set up and everything's plugged in and running, we fill it full of water, and then we move into startup. And so we're able to do that and fit all of this equipment into these small buildings, and then started it up late last year, and performed a startup sheet for each of the 5 buildings, and it's been running ever since. Can I
And
tell a funny story?
yeah,
Okay, so you mentioned it before how we had to come in midstream is because the architect attacked us. The owner, the housing authority, wanted an all-electric project, and the architect went around his back and my back and put a designed in with the mechanical engineer a gas boiler system. And when we found out, it was so frustrating because the owner had committed to zero net energy, and you can't do that with gas, that we were able to justify the extreme effort of going out and getting grants and getting this installed. And then when you finally had it installed, Albert, you recall that the architect and others gave us a ton of couple asterisks about how they didn't think the system was working because they just weren't even trying to start it up. Like they just, at every step of the way, this was a fight and like an unpleasant interaction with people who didn't believe in it and didn't want it to happen. And in fact, it works awesome. And it got done.
it happened. It happened regardless because we know how to make systems work, and they're simple. We're using ambient air to create hot water rather than burning a fossil fuel, and it's totally doable. It's totally possible. The funny thing was, I remember getting all of those emails, and it was such a simple thing. So the interesting thing is, if we go back to this picture, if I can get my screen to work now, if we go back to this picture. So you think about what's happening, right? In a normal building, we've got the heat pumps are making hot water. They're putting it in the primary storage there on the right-hand screen. And then they're giving that hot water out to the swing tank, and the swing tank's doing its high to low thing. And the hot water goes into the building and people use it and everything's fine, right? Any water that they don't use comes back into the swing tank, and the swing tank kind of cools down after a while and stuff like that. So that's a normal building that's got people living in it. In a brand new building, we start it up, we watch the system, we go into all the fixtures inside the kitchen and the bathrooms and the showers. We run the showers, we run the faucets, and we see hot water coming out, and we set the mixing temperature and set the recirc temperatures, and that's a factory startup by us. That's our people coming out there. And then we say, okay, you're all set, and we fill in our startup sheet and we go. But then if the building sits empty for a month, then essentially here's what happens, right? There's no hot water consumption, and you've got this isolating swing tank whose job it is to isolate those losses away. So when somebody starts coming in 2 weeks later to do a building test and check that the fixtures are going to work, they're not going to see full temperature hot water because we've isolated that away. The recirculation loop has probably lost all its energy, and the swing tank itself is kind of ramped down, and it'll take a while to ramp back up. So the solution that we had to give them when they're on site saying, hey, the water's not hot enough, you can't do it with heat pumps, we got to have gas, we got to burn things to make things hot. All we're really telling them is you get an 80-gallon swing tank, just use 40 to 60 gallons of hot water. Let it dump through the fixtures and everything will reset and you'll be perfectly fine. Because that's really all that had to happen, is they had to flush the cold water out of the system because the building just hadn't been occupied. And as soon as they did that, then, well, the phone stopped ringing and the building's still occupied. Nobody's complaining. So the system must have worked after that point. So yeah, that was an interesting point. So at this point, this is really most of the system. It was a super interesting project to do, and it was funded by the CEC in California under a tech grant. And part of the goal of the tech grant was for us as a company to come back and create. Let me see if I might have jumped out of my slides too far here. Was to come back and create this as a product. And so that's what we've done now by creating these additional measures. Let's see if I can get back to kind of where I was in the beginning. So part of the tech grant was, okay, let's let's use this building as a model on how we're going to build these adaptable systems that can be installed in these tight spaces. And by tight spaces, the real focus is existing buildings, right? How do we treat existing buildings when heat pump water heaters need more room because there's just more functionality to accomplish it rather than just burning a fuel? So we created the droplet program. And the very top line where it says on the left-hand side, droplet 2 is what's in that building at the Parkside Apartments. That's 2 heat pumps, 31 kBTU an hour. And then we just started building more. So we built an entire rack system, pre-engineered it, that can show up on site just like that. And it's a collection of heat pumps all put together on a rack that can just be set on a roof or bolted onto a pad. It's all pre-piped, so there's only 2 water connections. It's pre-powered, so there's a single power landing. It has a master staging controller. And by the end of this year, it'll also have the EcoPort. And the EcoPort is the box that the utilities are looking for, so we can really get these water heaters to work in the demand response, or in addition to demand response, which is the utility saying load up because we've got excess renewable energy that we want to place, and we can place it into the tank as thermal energy, or shed, which means we're entering our peak periods and we really want to reduce the amount of power being utilized on the grid. So just turn your heat pumps on and coast through that period on storage because you built that storage ahead. There's all sorts of interesting things that are going to go along with that, like how much storage you build, how long of shed periods do you want to cover. And then the other thing that comes up that these controllers will deal with is time of use rates, right? So if we understand that there's a rate structure in place where the most expensive energy is in this time period and the least expensive energy is in this time period, we can build a system out of a catalog design. It's a simple matter of storage and capacity. And we can set it up so that we can look at that rate structure and optimize the heat pump runtime to be at the lowest rate structure and build enough storage so that storage is available for use when the occupants want their hot water in the building. So those are kind of the 2 things where these systems are going. And very, very soon, not very far away, we're going to actually think about them as big thermal batteries that can be operated as a system. So that's where we're developing. We've got a lot of new control ideas going on that will pop out late this year, but much of it really started with this project. So, we're super grateful to the CEC and the tech community for setting it up, and of course, Sean for bringing it to us.
Well, you heard, I was really frustrated that the architect was foiling our efforts to do an all-electric project over the voice of the owner. So I want to thank you for stepping in and rescuing us. I didn't have any other solution. We had to, because your product is so efficient, you see that it's using half as much energy to get water heating done as all the other products we've been messing around with. And so since that project wasn't designed for electric boilers, heat pump boilers, right? We had such limited power that we had to only use the amount of power that was already delivered to the building, which meant we needed stand-ins. We couldn't have even tried using other products, most likely, without having to do a service upgrade, which would never have happened. So you really, rescued us. Thank you very much. And with the product that by every report is working great and everyone likes, which I have lots of other projects with central boilers that do not get that kind of rosy reputation out of the deal.
Well, so
let me jump in for just a second. I am surprised to see nothing in the chat, Sean, except the things that you put there, and then I sent something back to you directly. Did you do something magic to get in the chat, and are other people potentially blocked from getting in the chat, or is there some magic?
No,
somebody just went in.
I've been chatting back and forth with Zach Lawrence over at SMUD quite a bit. So just over in the chat, it works. And I'm having a good time.
Yeah, just so everybody that's on is just not. I've never seen one where there were not comments in the chat before, so I was afraid that you only use it in a magic way.
It's lunch hour. No, but actually, Zach did have his question here of: are the dimensions being shown on the screen accurate? Are those inches instead of feet? So I think you have like 60.
Yeah, no, they're wrong. They're wrong. Thanks for bringing that to my attention. Yeah, we set the template up, of course, for the skids, and the droplets need to be
Inches.
Inches. Yeah, and actually, we have a website, waterdropsystems.com, and it's got downloads with the correct specifications. All the skid submittals, sizings, weights, power requirements, all of that stuff is available. And then we're just finishing up another round of droplet drawings, but the information's there, or you're welcome to reach out to us. And that droplet 2 in Parkside was, about 60 inches wide at the long, 60, 45, 80. Yep, that's correct. Good catch, folks. Thanks. And so there's so much more coming. Additionally, when you think about power requirements and existing buildings, here's an interesting point. We'll leave with this point. But these Senko 2s operate on 220 single phase, right? So we don't need 3-phase power to operate these things. And in a skid, the only reason we bring 3-phase is either we have a whole lot of heat pumps and we want to balance the power across 3 phases, or we've got a big 3-phase swing tank. So we've been funded for the last year by the Canadian government and the province of BC to do research on phase change materials as thermal storage for CO2 heat pumps. And that research is winding up, and it's lining up for another DOE grant, for San Jose, California. And we're looking at a 74-unit building that will use phase change storage instead of water storage. This plant will still have 3-phase, but what's going to happen here is we're going to have a chance to understand how to build these thermal batteries. And when we build these thermal batteries, we're going to find buildings, smaller existing buildings, where we can retrofit the domestic hot water system with single-phase power and a low amp draw, because we won't need a big swing tank if we can get this phase change working right to replace the swing tank. That's actually a pretty big deal when you think about what the needs are to retrofit buildings and provide electrification. One of the goals for us is to have the lowest amp draw and the lowest connected load, so that these buildings don't have to mess with bigger panels and bigger transformers, and can get into car charging and space conditioning, as well as domestic hot water heat pumps.
I want to add to that. And Zach, I saw you thumbing up there. It's like, because you've probably been to one of the heat pump boiler thing that SMUD did back in 2019. Anyway, quickly, is that there have been a number of heat pump boiler retrofits funded by low-income weatherization program, like dozens, right? And certainly in the early years, they were not taking out the gas completely. They were leaving it behind because they didn't feel like they had enough heat pump capacity in the existing building because of wiring limitations to meet 99%. So they were like, we think this system will meet 96% or 92%. We're going to leave behind the gas boiler. And they're talking a percentage of the peak. It's all about the peak. And so what Albert's saying about having a phase change material in there as a thermal battery that can be deployed during peak allows us to then keep the existing wiring system in there, because most of the time the building is not on peak. And if we just have a little battery for peak, then we can use the existing infrastructure with no drama. That's a really,
as a company, we're really excited about it.
I see so many people playing with phase change material, and it's a really core insight into how to do a system right. It's to store energy. It takes some research, and but as a company, we're really excited about it, because when you think about this time of use and demand response, and the fact that we have the possibility to manage these things as big thermal batteries on a grid that can be useful tools in balancing the grid or shaping the load on the grid. The interesting thing with phase change is the other benefit that we can get is we can store all the thermal energy that we would have in a big tank of water in roughly half that physical size, which means it makes it easier to do retrofits if you only have to bring in
a tank that's half as big, or if you bring in the tank, same size tank, now you've got a lot of extra storage that you can build out for demand response and time of use management, which means that you can actually save money by using a larger storage vessel and using time of use to the maximum advantage. So there's a lot of cool things coming down the line. It's no longer just get a steel tank and bring a pipe full of fuel in it and light it on fire. We're just way beyond that.
Well put. Well, I think that we're at that point. We got 1 minute left. My computer's about to die. So
I'll do it.
It was a total pleasure. Thank you, Jay, so much for hosting us. Thank you, Albert, for sharing your brilliant engineering knowledge of how to get these systems done right. And thank you, all of you who attended, for being interested in such a nerdy, super important topic. So thanks, y'all.